Hi everyone, welcome back. Today we're going to finish off the content from our section on quantum numbers and orbitals. We're going to be looking specifically at orbitals themselves and focusing on these last few learning objectives. So pause the video, read over them, and then we'll move on. So we left off looking at the rules for determining quantum numbers. And this is a pictorial representation of orbitals. We talked about how we looked at the 1s, the 2s, the 2p, the 3s, the 3p, and the 3d orbitals. And what's not shown on here, we do have the L values represented. We have N and L, and these boxes tell us information about the M sub L. And all combined, this is an orbital. So we see we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 orbitals within the first three shells of hydrogen. And it turns out that for hydrogen, the energy of these orbitals is dependent only upon the principal quantum number. Thus, the energy only is actually predicted by the Bohr model. Since it only varies with the n value, the 3s are equal to the 3p and are equal to the 3d orbitals. The term that we use to describe the orbitals that have the same energy is that they are degenerate. This means same energy. So the 2s are degenerate with the 2p orbitals, and the 3s with the 3p, which are degenerate with the 3d orbitals. Let's take another look at orbitals. We saw already how they were represented, those kind of fuzzy green balls, and so now we're going to look at them again. So remember when we talked about orbitals and how they are, if we take the wave function and we square it, we get the electron density. That's what these three graphs on the top represent. These represent electron density. If you take that and then you rotate around into 3 dimensions, you get this pictorial representation. These are 3-dimensional representations of the electron densities. And what we can see is that we talked about nodes earlier, that there are regions where there's no electron density. And in these pictures, that corresponds to the white regions. The white regions are the nodes. And that's where there can be no electron density at all. There's a mathematical number that describes the number of nodes, and that's that the number of nodes is equal to n minus 1. So if your n equals 3, your number of nodes is 3 minus 1, or 2. N equals 10. Let's erase that. If n equals 10, your number of nodes is equal to 9. Okay? And so we've got different representations of the node, or of the electron density. We have 1s, 2s, 2p that look essentially like spheres with smaller spheres inside. And then we also have the p-shaped orbitals. These look somewhat like dumbbells. And these spatial distributions of orbitals are based upon graphing the electron density in 3 dimensions. In reality, there is a non-zero chance that an electron is going to be infinitely far from the nucleus. But because that chance is so small, we often ignore it. And so we represent the orbitals with these boundaries. And these boundaries represent 90% of all electron density. Let's take another look at the different orbitals. So we see here we've got the sphere shape for the S shape for the S-type orbitals, whether it's 1s, 2s, 3s, 4s, etc. The p orbitals have more of a dumbbell-shaped look to them. This is another way that we've represented it. Again, this is showing our 90% of all electron density. We cut off a boundary somewhere. These planes, these represent the nodes. Oops, excuse me. These represent the nodes. And we can have planar nodes or conical nodes. And then within, if we go back and look at these are called radial nodes. And that's because they're out at a certain radius from the center. So we talked about the orbital names. We've got our S, P, D, and F orbitals, the numbers of each kind, and these come from the rules, remember. Orbital name, that is our quantum number L. The m sub L value dictates the number of orbitals. This ranges from negative L to positive L. So when L is 0, 1, 2, or 3, we can have negative 0 to 0, or just 0, negative 1, 0, 1, negative 2, negative 1, 0, 1, and 2, and then negative 3, negative 2, negative 1, 0, 1, 2, and 3. Let's erase that there. Corresponding to the numbers of orbitals. And we see here these different pictorial representations in 3 dimensions along different planes. We saw that the S-shaped orbitals are spherical, the P-shaped orbitals are dumbbell, or the P orbitals are dumbbell-shaped. The D orbitals are mostly cloverleaf. It looks like 4-leaf clovers, and this dumbbell with a donut in the middle. And then the F orbitals are too complicated for us to deal with. You don't need to recognize them, although if you want, you can look them up on the ebook. There's an app in the lesson 2.5 that will show them to you. So all of these orbitals that are the same subshell they are degenerate, which means they have the same n and L values. All 5 of the d orbitals within the same subshell are identical in energy and therefore are degenerate. The change in coloration that you see, and here we use orange to green, that's when we pass through a node, it changes colors to represent changing from one orbital or one end of the orbital to another, keeping in mind that the node represents where electrons cannot be. I recommend that you find the app that's in lesson 2.5. There's the section on d orbitals. So it's right near the bottom. And this allows you to quiz yourself on orbital shapes and the quantum numbers. I recommend that you use that to get some practice. Speaking of practice, we're done with this content. Let's move on to some problems to give you an opportunity to think through this. So, which pictures represent orbitals where n equals 2 and L equals 1? Well, so let's remind ourselves that N describes the size, whereas L describes the shape. And so you could try and differentiate based on size and based on shape. Probably the most important factor to look at initially is just the shape. So if L equals 1, that means that it's a p orbital. And if it's a p orbital, then it looks kind of like a dumbbell. So that eliminates 5, 3, and 1. So 2 and 4 are our p-shaped orbitals. Now for some practice, let's see if you can figure out what these other ones are. This here is a D-type orbital. It's the one that has the dumbbell with the donut. This is a clover leaf, so that's a D orbital, and this is a sphere, so that's an S-type orbital. Okay? Take a look at a different problem. These are just the different designations. The ones that are in the way I'll write. You've got dxy and dz squared. You do not, I repeat, you do not need to be able to recognize that this is a dz squared as opposed to a dxy, but you should recognize that they are both d. So which orbitals have the fewest nodes? Remember what we said about nodes. Nodes is equal to n minus 1. And so if we look at the orbitals in these different subshells, the lowest S subshell is a 1s. That means n equals 1, and there are 0 nodes. The lowest energy P subshell is a 2p. That means n equals 2, and so that has 1 node. And our lowest energy D subshell is the 3d. That means n equals 3, and it has 2 nodes. So the answer to that has to be A, that the lowest energy S subshell has 0 nodes. Now, in case it wasn't intuitive why these are the lowest, remember our rules. If we want an S-type subshell, that means L is equal to 0. N can therefore be 1, 2, 3, etc. And if we want the lowest energy, that means the lowest N value. N equals 1. For a p-type orbital, we know L equals 1, which means N has to be equal to 2, 3, 4, etc. Lowest energy is 2, and a D has an L equal to 2. Lowest energy there is 3, because we have to have an N value greater than our L value. Okay? Now you try one. Go ahead and pause the video and try this problem on your own and then come back. Welcome back. All right, so shown below you've got some quantum numbers and 4 orbitals of the hydrogen atom. We want to rank these in terms of increasing energy. So something to note as of right now, we're just talking about the hydrogen atom. Within the hydrogen atom, only the N value determines the energy. And so because of that, all we have to do is rank them based on their N values. And so 2 has an N value of 2, that's the lowest. 1 and 3 are the same, and 4 has the highest N value. And so that gets us B. Doesn't matter what order you put in 1 and 3 because they're equal to each other. Now, here's a follow-up question. To which subshell does each of these belong? Pause and try it on your own. Welcome back. All right, so let's remember what a subshell is. Subshell is defined by the N and L value. So we need to look at both pieces of information. If N equals 3 and L equals 2, that is a 3D subshell. N equals 2, L equals 0 is a 2S. If N equals 3 and L equals 1, that is a 3P. And if N equals 4 and L equals 1, that is a 4P type subshell. That's it for today. Thanks for watching. If you have questions, ask on Piazza or come to office hours. See you next time.